Okay, so last time we were doing the programming with conditional jumps. This is what we were doing. This was check if it's like less than 10, right? If the value is less than 10, output a 1 or a 0. I can't remember what I said, but let's see what the code says. We start with, let's make sure, is the audio working? Yeah. 1f, load the value from f. Okay, what value is in f? 5. I put a 5 here. If I wanted to test a different value, I would go and change whatever this is. I can make this whatever I want. This is like a variable value. I just put in a 5 for an example. If you remember in the previous example, this was like question marks, right? I just can't do that for an actual concrete example. Can you see that? Enough? Is that better? Okay, there you go. For A, that's load into B direct the value A, 10, okay? 8, that's subtract. Of course, there's no operand. It's just subtract. So what's the difference between this value and 10? If it's negative, we know that the number is less than 10. So I say that's JMP significant. It checks that leading bit. If it's high, in this case, it would mean it's negative. So if it's high, we're jumping to 6. 0, 1, 2, 3, 4, 5, 6, right here. And that says output, or send to the output register the contents in E, which is a 1. F0 halt. If this didn't trip, this acts as a no-op. If that significant bit is not high, we do this. We skip, we don't go anywhere. We just carry on. It's a no-op. DD, send to the output register the value in 15, 0, halt. That's it. This now checks it. Now, of course, you're looking at this, and you're left going like, yeah, okay, but okay, let's make this a little nicer, right? What could this look like? All right, well, let's explain each line of code. Load the value from address 15 to register A, load the value 10 to register B, calculate the difference, jump to address 6 if the significant bit sign flag is high, output the contents of register 13. That should say address 13, not register, address. My mistake. Output the contents of address 13, output the contents of address 14, and halt after. If you remember, we also talked about how some people don't like having 2 halts, and that's entirely fine if you're one of those people. There's an easy solution here. You just have like a jump always to that halt, and then you only have 1 halt. Same difference, but whatever. Not like you save any RAM in this particular case, but it does eliminate having 2 halts. Cool? Yay, look at that. So now, like we were saying, we now have, albeit limited by the fact that there's only 16 bytes, our system is computationally complete. We can loop, we can do branching, we can do like everything. If we had more, all that we could do is more of the same. If we had more than 16 bytes of RAM, if we had a bigger bus, whatever, I could add additional hardware as well, maybe new instructions. We could add more, but the point is, computationally speaking, there's no core thing that this can't do that something else could. You could say, we don't have multiplication hardware. You're right, but we could do it in software. We don't have division hardware. You're right, but we could do it in software. Like all of these types of things, it's sufficient to be as computationally powerful as like this thing. But again, limitations are really the amount of RAM we have. We got like the clock speed too, I suppose, right? But that's just clock speed. Really, the big thing is the amount of RAM. If we had more RAM, I think the next big thing, like if we had more time this semester and I had more RAM, I think the next topic would be the call stack, right? You should all know what the stack is, right? I'm not talking about like the abstract data type stack. I'm talking about the stack that your system has, which you would have learned about in 162. Maybe I even briefly talked about in 161. But in 162, you would have learned about the stack. If you've ever run a debugger, Raise your hand if you've ever run the debugger in like Java or Python or something, right? And then on like the left-hand side, do I have like I don't have one open. On the left-hand side, if you're using like IntelliJ or some other JetBrains thing, you'll always see like, when you're using the debugger, you can often see the call stack, which is like this function called this function, that called this function, that called this function, and this is where we're paused. That's the stack. We could implement such a thing. So we could create like functions in our code and in our machine code and everything. So we could create a system stack as well. We're not going to do that here. That is not a limit. The fact that we don't have a stack like that with this system, as a consequence of only having 16 bytes, is not a limiting factor in the sense of like computationally what it can do. It's just that the system stack, we all know that like having things like functions makes writing code easier. But you don't need functions. But imagine doing all your stuff without functions, right? That'd be painful. So like a stack is something we could have implemented, and I think that's where I would have gone next. But we don't have that right now. So any questions about what we've done so far? Oh, not that. There. Okay, we have a complete system. Now, we started with binary, right? Then we learned about transistors. And we worked all the way through various components, sequential, combinational logic, registers, RAM, adders, program counters, output displays, lookup tables for programmable logic. All of this we built to make this system that we are programming with machine code. The whole point of this class is how the hell do these things work? And we've learned most of that. But there's still a gap. Because when you write code, like how many of you have written machine code before this class? A little bit? What were you doing?
I was just messing around.
You were messing around? Well, other than this guy right here, no one, right? So, because when you're writing code, you write code like in Java or Python or some other high-level language. Now, when you look at a language like Java or Python, that's actually a very, very high-level language, okay? Because, you know, traditionally, okay, we've got machine code. When you write in something like C, for example, raise your hand if you've ever written in C, regular old C, okay. So for those of you that have, C is a traditional, you know, you write it, it's very similar to like the syntax like Java and Python, very similar syntax. Those are like C inspired a lot of the most popular syntax we use. That code is compiled into machine code, okay? So all of the lines of code you write, your for loops, your variables, your if statements, all of that gets compiled to machine code. And in fact, if you ever wrote like a simple hello world program in C and you compiled it, you can actually look at your machine code. You can look at it for your processor, which is pretty cool. There's also some settings for your compilers in C where you could actually assemble it to something called, or compile it to something called assembly, which we're about to talk about. Assembly, let me draw. Like, this is not going to be accurate, but it gives you the right idea. We have machine code. I'll call it MC for machine code, okay? And what we like to do is we have this thing called assembly, which makes writing machine code a lot easier. Now, easier is a relative word, and it's, you know, in the eye of the beholder. But it's really not that sophisticated relative to the machine code. It's effectively a bunch of mnemonic tags. And you already made a cheap one in the last lab where you just did like a find and replace, right? To make coding and assembly easier, which we'll see here really shortly. But then we have something like C, which is compiled, okay? So there's a lot of steps to go from something like a for loop to what's the underlying machine code. We're going from assembly to machine code is they're like adjacent to each other. They're the same thing. There's really not much going on there, but it does help. But of course, even though it makes things easier, we prefer languages like C, higher level languages, because it makes programming even easier. Now, on top of that, we have languages like Java, for example, which when you compile it, it doesn't compile it to the machine code. Really what it is, it has this virtual computer and it compiles it to the bytecode that runs on this virtual computer that runs on this, and this can be changed depending on your, it's a whole thing. So they definitely are a lot more sophisticated now, don't get me wrong. But the abstract idea of we go from high-level language to something that runs on your system is like the compilation process. But there is this like in-between step that we just skip over. But you can set settings on C to compile straight to assembly, and you can look at the actual assembly, which is pretty neat. Also, compilers are sophisticated. They do things like, it'll like optimize your code and everything as well, which is really nice, but anyways. So we're going to go here. If we were to take the next level, like look, the whole point of this course is how do these things work? And I hope you get a sense of how they work now. In fact, you better understand how they work now. In order to go from that, from like bits, transistors, to here, and to go from like compiler, we could have a whole course on compiler construction. Okay, so that one last gap is something we ain't gonna hit right here. I'm sorry. Maybe one day, I don't know, but it ain't happening. But we could talk about assembly to bring it one more layer of abstraction up from how we interact with our hardware. Instead of doing the hex codes, the binary effectively, the machine code, we can program in assembly, another layer of abstraction higher. They're very, very similar, but it is another layer of abstraction. So we're abstracting as close as we can to how we are used to interacting with our computers when we write code. Okay? Okay. So, with the ability to make decisions, the ESAP system is complete. However, it's not particularly easy as it's programmed with machine code. It's not that bad. We have 16 instructions. We can remember it all. But at the end of the day, there's some like extra like brain power required to be like, I want to load. Okay, do I want 1 or 2? If that's, you know, like you got to think about it. And we all know that like whenever you're writing code to solve problems, solving problems with code in and of itself is already a tricky task, right? Writing programs is already challenging enough. So let's make the programming experience as easy as possible. Like, let's eliminate all the pain and suffering about programming to make the programming experience go that much better. Would you agree that's a good idea, right? Programming's hard enough as it is, thinking about these things. But let's make the whole experience of programming better. And if you're like, I don't know, I don't buy it, then go program in Fortran. Right? Because the whole point is we've made programming languages better and better and better and better. Eye of the beholder again. But easier to work with to make writing programs easier, right? Because it's better that way. We like it that way. This is a big goal of like programming languages. How can we make the experience better? Machine code is also like, it's prone to errors and it requires memorizing bit patterns, or hex codes, fine, right? And like an error is harder to see if it's because you misremembered that like a 3 and a 4, oh, 3 was actually load A direct and 4 was load B from right? Like there's so much more complexity if you're memorizing machine code. So we want to improve the way programming is done. So instead of writing bit patterns or hex numbers, we're going to use mnemonics instead. Little tags. In fact, we're going to use the little tags that we've been using to refer to these instructions already. And we're also going to do some other quality of life features in our assembly system. Things like separating opcode mnemonics from their operands. Also, how we interact with like literal values could be a little nicer. How we deal with negative numbers can be a little nicer. So we're going to do a couple little things. There are a couple of features of your typical assembly language we're not going to include here just because it's a little overkill for our needs because we only have 16 bytes. But we're going to include a number of the big features that a typical assembly language has. So an assembler is like a program that assembles. It doesn't compile. It assembles your assembly language to machine code. Assembly language is very low-level programming language. It's basically machine code plus, okay? It's often referred to just as assembly. Assembly is strongly tied to the specific system design in the underlying hardware and its respective machine language. For example, the instruction set for the ARM processor, right? Anyone here have like a Raspberry Pi or anything? Yeah, well, this is what, chances are it's using an ARM processor, right? And you can go learn all about the assembly language for the ARM processor. So you don't, are they now? Yeah? Wild. Huh.
That's why so many video games don't work on it.
Yeah? It's a cool instruction set. So if you wanted to start programming for a different processor, you don't really need to, it's good to have like a general idea of like what the underlying hardware is, and you can find like a high level schematic where it'll be like program counter, this, like kind of like that design that we always saw, right? Where it was like program counter, ALU and whatnot. But you would look at your instruction set, which option, like what instructions you have available, what registers you have available, and how a couple of those instructions work. And then you're good to go. You can program in like in a different instruction set, and you can use an assembly language like the ARM one. Now there's a couple of different like settings for it. If you wanted, you could do x86 as well, right? Now you can't unless you had like an emulator. But if you wanted to do ARM, you can't, but he could, right? So like it depends on what your underlying processor and hardware can run. This is another pain about like assembly code. Like if I write code in Java, I want it to work on everyone's computer. Not for yours because you have an ARM processor, or yours because you have an x86. That's a nightmare. Well, that's where like all this crap comes into play, right? It kind of manages that stuff for you. But anyway, I was actually at a bit of a predicament because I was like, well, if I run out of content to go through this semester, I could go deeper into assembly language. Like, okay, we learned everything, but now we're going to program in assembly. But what assembly language should we use? x86? Well, that one, like everyone would have access to except you, I guess. But the problem with that is like that's a big boy right there, right? Yeah, that's entirely unnecessary. It's good, don't get me wrong, but there's a lot of like funny things about it. ARM is nice and clean, and it's gaining popularity. It's really good. But again, like you could run it natively, but the other ones you'd need like emulators to do it, which is fine. But now it's kind of a pain in the ass, and people are trying to get emulators running, and it's a whole thing. So I didn't really know what to do. There's a popular learning one called LC3, Little Computer 3, which is actually pretty nice. It's the one I learned on, but it's still kicking. Anyways, and it's really popular, so much so that people wrote like C compilers for this like instruction set that's just entirely bullshit designed for teaching, but you know, geeks are geeks, right? They'll do that type of stuff. Anyways, here's the ARM processor. Here's some like what registers there are, right? Here's an example of like how to add, and anyways, you can go through it if you really care. All right, so an assembler is a tool to convert assembly language to machine code. So we have like assembly language or assembly, and then we have an assembler. An assembler assembles the assembly to machine code. When compared to machine code, it really does give a more like human-centric way of programming. But if any of you are sitting there going like, when you look at the assembly and the machine code and you're like, but it's exactly the same. Yep, but you'll have to admit it's a little nicer. So assembly is effectively machine code, but with just a couple of nice features. It has many benefits over programming in machine code, but the two key features are the mnemonics from referencing specific instructions. For example, loading the value 5 into register A instead of the machine code 001000101, or like whatever the hex value of that is. You could write like LDAD 5, load A direct 5. Like what's nicer, this or this? Obviously this is nicer, obviously, right? And if you say this is nicer, shut up. I know it's not, we all know it's not, you're not impressing anybody. This is annoying. The mnemonic would mean the same thing. It literally is like a find and replace. You don't even need to write an assembler. You could go to Notepad++ and press Control-R and use find and replace for the bit patterns and the tags, and it'll work fine. but it's nicer. It's easier to remember and like mentally parse. So not only is it like nicer to write, like you got to think this is a two-way street. Like when you're writing code and you're like, I want to load, okay, I know load, that's 5. Okay, so I need to, like you could do that. But it's also not just about writing the code, it's about reading the code, right? When you read the code and you see load, oh, that's load a direct 5. All right, it's a little nicer. Another big key feature that we're not going to include, only because we have such little amount of RAM, it's kind of overkill. Maybe there's an argument to include this. I didn't bother. What we could do is we have like labels or symbolic representations for memory addresses. So instead of saying like jump to memory address like 17, which I know we don't have one, but let's say we did, jump to memory address 17, I could go in my assembly to like the line where that would be, and I would say like, this is where I want to jump to. And then above I would say like jump to, this is where I want to jump to. And the assembler would go like, well, that's memory address there. And so, okay, it's still another find and replace effectively. It's a little nicer. So yeah, memory addresses could be labeled and referenced by their label. This would make referencing memory addresses for jumps and loading from RAM a little easier, nicer, but again, that's overkill. It removes the need to remember specific memory addresses. Then also like it gives like some power to your assembler to move things around. But anyways, it also removes the need to constantly update addresses when lines are added or removed. Raise your hand if you're done the assignment. Like when writing the assignment, did you ever like write a line and you're like jump to this memory address, and then you inserted a line like below or above, and then you had to go and like update where it was, right? Like if I say like jump to like 7. Right, and then down here is 7. But then like I insert 2 lines here, this would need to be updated to 9. But if I forget, it's a whole to-do. That would eliminate the need for that, which is of course nice. Okay, an assembler would take the assembly language and translate it or assemble it to the corresponding machine code. It's just like a find and replace. It replaces the mnemonics with the opcode bit patterns and translates literals to their binary or hex values or whatever. It would replace all labels with the assembly with the corresponding memory addresses as well. So that's like the core thing here. Typically, each statement in assembly has like a one-to-one mapping with a statement in machine code. Typically, there could be some funny little things depending on the instruction set or whatnot. But for our assembler that we're going to build, it's going to have a one-to-one mapping. And despite its simplicity, it definitely improves programming experience and allows for a small amount of abstraction, right? So here's an example of that. This is the program for, is it less than or greater than 10, right? Here's like what the assembly could look like. Load A from RAM, the address F. Load B direct, the value 10. Subtract AB, jump 6 if the difference, the S, out UD, halt, out E, halt, right? But what's the machine code? That's the machine code, right? Well, one thing you might notice here is like I've got 0, 1, 5, right? Why do I have 0? Well, this is what I want to output if it's not less than 10. This is what I want to output if it is less than 10, and this is the value I care about. And these are all no-ops because it's just there's nothing there, right? That's just like, that's unused RAM. But in the machine code, it's all the same. And it's just kind of funny that the 0 and the 0 are the same, but that's just, it's about the intentionality. That's kind of a nice thing about assembly, is you could be like, I didn't need to put a 0 here. I could have put a no-op. It wouldn't have made a difference in terms of the machine code. Yes, but, it's about like intentionality. This is what I want to output. This is what I want to output, depending on the case. This is the value I care about, right? Yeah. So, yeah, basically, I have this assembler. This takes my assembly language. It assembles it to the machine code. Pretty straightforward stuff. Right? Right? Right. Any questions about this idea? Would you agree that it at least gives us, although the smallest bit, it does give us just the little bit of the ability to abstract a little bit better, right? We've got one more layer of abstraction. This is the last one we're really going to hit this semester. So let's make an assembler. To make programming a little easier for our system, we're going to make an assembler for this ESAP system. All an assembler is a program that will translate the assembly to the machine code. It's a program, okay? Now, it would have been amusing if we could somehow make make a program for the ESAP system to assemble code for the ESAP system. We're not gonna do that, right? That's just too much. That would be cool though. That would be really cool if we could, but we're not gonna do that. So the ESAP assembler will only implement the mnemonics and interpret various literal value encodings. It will not make use of the labeled memory addresses, just because that's just too much. The mnemonics make writing programs much easier. It will also make interpreting reading programs easier as well, right? Like we just said, load A from RAM 15 is a little nicer than that, right? Right. So what are the mnemonics? The ones we already talked about. No up, load A from RAM, load A direct, load B from RAM, load B direct, save A, save B, add A and B, subtract A and B, jump always, jump Z, jump S, jump C, out unsigned, outsigned, and halt. Those are the tags we're already used to. Let's use those tags. So the assembler will translate literal values to, from various bases as well. So here's a nice little thing about our assembler. I can write, as a programmer, I could write this, or this to mean 10. That's what I'm going to allow it to do. Now, as far as the ESAP system wants, it wants the machine code for 10, right? So like, you know, we were always using hex. So like, it would translate it to 10. But so our assembler would have to go like, okay, well, is this a base 2 number, a base 10 number, or a base 16 number? And then know and process it accordingly. But why? Well, it just gives the programmer a little bit more flexibility and intentionality in their code. Like if we go up here, you can see in this example here, I said load A from RAM OXF, and then here I said load B direct 10. I could have said OXA, that's fine. But why did I do it that way? I don't know. I mean, I did it that way because, I don't know, I felt like referencing memory addresses made sense, hex. Like this, I don't know. Then again, I don't know why I didn't do jump S, like OX6. I don't know, maybe I should have done hex there. That makes a little bit more sense. But the literal value 10, I don't know, I just thought decimal, right? These are all the literals I care about. Long story short, it gives me flexibility as the programmer. I can do it however I want, which is nice. Okay, there's the labels. Negative numbers will also be handed. The assembler will convert the numbers to a 2's complement number, which, by the way, is stupid in Python. Python is weird. So we're going to see some code. I wrote the assembler in Python, which runs on x86. Well, which runs on its bytecode. It's a whole thing. But in Python, it doesn't store negative numbers the correct way. It does it its own way because it's Python. Therefore, you will see some really weird code where you're like, that's how I have to? Yep, I know. Just deal with it. It's Python's fault. It's not anyone else's fault except Python. If this was another language like Java, I'm sure this would be easier. But because it's Python, converting to 2's complement, it's weird. It uses a sign bit, right? That's what it does. Because everything in Python is like an object. So integers, like even though, oh, it's a primitive type, it's not. So it stores it always as an unsigned integer, but it has a sign bit. So then if you want to convert that to 2's complement, it's such a to-do. You'll see. It's not that bad. I'm just warning you that you're going to see it's peculiar. Because I spent so long wondering, like, why is this not working? I just said, give me the bit pattern. I know this is a signed number, Python. Give me the bit pattern. And none of my code worked. It made no sense. And it was because I discovered later that Python is stupid. So anyways. Our assembler will also do a little bit of error checking for us. You know, we'll do some, like, check if the program will actually fit into RAM. If you try to write 17 bytes, it won't let you. It'll do some basic syntax. It'll check operands if they're missing or if the values are in the correct range. We'll do some basic error checking. Not necessary, but it's a nice feature to have. And since it's just a program, any programming language to make an assembler will work. So we'll use Python, which maybe in retrospect was a bad idea. I don't know. So here is a discussion of a script I wrote in Python that acts as the assembler. And we'll talk a little bit about it so you can see. The script is by no means the only way one could or should make an assembler. It's just to show you of what it could look like, okay? It facilitates the additional layer of abstraction. So this is that box, right, that takes the assembly to the machine code, okay? We're going to start with a couple of constants. You'll notice operators, it's a dictionary from tag to bit pattern, tag to bit pattern, tag to bit pattern, okay? It's just a dictionary. Basically, this will serve as the find and replace. I've got this set. It's just the number of, it's the instructions that take an operand. Basically, if your instruction is in here, we need an operand. If it's not in here, we don't need an operand. Valid syntax. Here's a bunch of regular expressions. If you don't like regular expressions, don't worry too much. It just says, like, basically, if you see this, every line in your assembly that you get, if it doesn't match one of these, it's not valid. Okay? And this is basically like, okay, oh, load be direct, okay, and then we've got, okay, it's a number, and the number can be like this, or like this, or like this. Anyways, that's just basically what it's doing. So there's some constants to just help make programming a little easier. We'll also have a couple of functions. Originally there was more of an explanation in the topic about each of these things, but I figured it was perhaps a little overkill. Here's a function, parse number. It's going to take a number, but remember, everything it reads in Python is going to be a string, so we need to take a string and convert it. So what we're going to do, basically, it's kind of cheesy, and this is very unsafe to do because whenever you say eval, this means take the string and evaluate it like it's like a line of code. So you could like write like naughty code in your assembly language, and then eval would like run it, and it could cause problems on your system. So it's a very it can be very unsafe, but don't worry, we'll do our regex checks first. So like if there's any naughty code, we would never get to that. But anyways, just for those of you that know, I know this is bad, but whatever. Basically, take that string and run it. What's nice about this, if it's the string 10, have you ever run the line of code in Python that says like 10 and you hit run? What do you get back? 10. That's it, right? Here, let me. Here. Whoop. See, if I run the line of code 10, what do I get? You get 10 back, right? Yeah. If you say eval 10, well, that's just silly. Evaluate, this just, oh, it's eval. Oh, it must be a string. Perfect, perfect. There. Right? But what's cool about this is I can say ob 10. It gives me the 2. It evaluates it as like that. So this will actually do the conversion for me of the bases, which is really nice. That gives me 16. I think you can also do like oh. Yes. Anyone know what that is?
Base 8.
Yeah, you should be able to know because 1, 0, and whatever base always gives you the, yeah. Now, our system is not going to be designed to work with base 8. It's entirely unnecessary, but, you know.
Why is there no?
Why oct, yeah. There might be others. Pardon? Octa. What is base 8 called? Octal? Octal? Fair enough. Yeah, I buy it. Yeah. Anyways, it could do that, but it could also do like oh, I need right? So now like I evaluated that string, and now if I could put a whole really bad program in there that will get run. But Anyways, we won't do that because we're good programmers, or we're nice.
Right, in the Python way to execute like a shell.
Of course, to do a fork bomb and
RMRF.
yeah, we could. So we're not going to do that though. So we evaluate it and convert it to an integer. Remember though, when Java or Python or any language is storing an integer, and you're like, it's a 10, that's a 1 and a 0. Well, not really. It's storing this abstract value 10 that it encodes some way. When I want to write it out, I have to like tell it how to encode that value, right? So don't get too hung up on the fact that like, well, that'll store the number 1, 0, or like if you put in an A, and you're like, well, that's storing it as the number 10. Yes, but 10 is A, right? Don't worry too much about the encoding. And by the way, because of how this works, because of our regular expression strings, it'll only ever accept hex, binary, or regular decimal values, okay? So oct, even though like that could work, it's not gonna. We're not gonna bother with it. So this is an easy way to just, I don't care what base the number is, get the number, okay? Otherwise, I can't parse that operand, right? Cool, great, awesome. Another way, verify number and fix negative. This has a long explanation because I'm mad about Python's negatives. Basically, all right, let me see, it's been a while. Okay, if number is less than 0 and the length of the binary version of the number plus 1 is greater than max bits plus 2, or I don't remember. Honestly, I can't remember right now. I don't know what this is doing. Or if the number greater than or equal to 0 and the length of blah, blah, blah. Okay. Okay, this is basically saying if the number that you gave, if the number is less than 0 and the number of bits we have is more than the number of bits, the number of bits that that number requires to represent is more than the number of bits we have plus 2. The plus 2 is there because when you ask the length of a binary number, it includes the 0b. So that's what the plus 2 is, by the way. It's actually weirder than that because I think it might also include like a negative sign. It's a whole thing. If the number is greater than 0 and the length of it, okay, yeah, it's the same idea. If the number, the plus 1, number plus 1, why is the plus 1? I can't remember what that is. It's probably explained in here. Negative numbers are represented in max bits minus 1, but require plus 1 for the negative sign. Yes, okay, that's stupid negative sign. Anyways, this basically checks, is the number that you want to represent, I have 8 bits. Will the number that you want to represent, like, does that number fit in 8 bits? If you give me the number 1,000,000, this is going to go, no, it don't fit, okay? It checks for positive and negatives. This would also work for the 4-bit operands too, like load direct, okay? Cool. And then if the number is less than 0, what are we doing? We are doing 2 to the power of max bits minus 1 to get a bit string of, why minus 1? Max bits minus 1. 2 to the power of 8. Yes. So we get, yes, perfect. So that'll get us 1, 1, 1, 1, 1, 1, 1, 1. If this is 8, 2 to the power of 8 minus 1 will give us all 1s, right? 2 to the power of 8 is 256, right? I want 255. 1, 1, 1, 1, 1, 1, 1, 1. I've got all 1s. This is the stupid thing I have to do to make Python give me a 2's complement number, okay? So I get all 1s, and then I exclusive OR it with the number times -1. I multiply the number by -1, so you know, if the number is like -7, I make it 7. I exclusive OR it with that. Remember what exclusive OR does? If it's all 1s and you're exclusive ORing it, what does exclusive OR do? Come on, we did this on an assignment. We did it in labs. It bit inverts. It acts as like a bit inverter, right? Think of it like this.
You're basically making the number positive and then doing how we made.
What we're doing is you exclusive OR it and add 1. That's 2's complement. You bit flip, add 1, 2's complement. We're just like forcing it to do 2's complement. This part right here, taking it, so what we do is we go, okay, 1, 1, 1, 1, 1, 1, 1, 1, right? First, if I have exclusive OR, this is a 1. This is the 255 here, right? 255. That's what this is here. Why did I need to do this? Because this forces, because Java or Python will try to store integers in an arbitrarily large number of bits. So like, you know how it's like, oh, in C, we have 64 bits to store our integer. Well, what if you want to store a 65-bit number? Well, you need to use like a long or whatever, right? Python doesn't have that limitation. It can store hilariously large numbers because it just arbitrarily like can have more bits. So in order to force it to have a certain number of bits, you do like you do a Boolean operator on something with the number of bits you want. So I do this. If I have 1 and a 0, 1 exclusive OR 0, what do I get? 1. If I have a 1, I get a 0, right? So exclusive OR is acting as like a bit flip. So we get the right number of bits, all 1s, exclusive OR it with the number times -1, because if the number is like -7, this is what it wants to do, right? Like Python's like, oh, it's a -7, right? That's what it like thinks. It's really weird. That's a 0. Okay? So what I do is I say, okay, just whatever, exclusive OR it, these get padded, whatever, you bit flip, 1, 1, 1, 1, 0, 0, 0, 0, you add 1, 1, 1, 1, 1, 0, 0, 0, 1, that better be positive, or -7, all right, in 2's complement. I really hope it is. If not, I don't know what I'm doing, but it does work, trust me.
Question.
Yeah.
Couldn't you just check if the number is less than 0, convert it to the 2's complement, and then do the check of whether it's too many bits?
Oh, maybe. Yeah.
Then you wouldn't need cases.
Oh, maybe. Try it. Yeah, perfect. Yes, good. It's 7. Okay, anyways. Yeah, and we'll pick up here on Friday. Okay?